My name is Markus Murschitz. I'm working at AIT at the Center for Vision Automation and Control, and for me that is really important because in the topics I'm working at, the control part also takes a more prominent role than in most of the talks we have been hearing about, because it's very robotic. So what I'm talking about is automated loading and how it can help us to get over the problems we have in loading scenarios, especially if we think about the last mile problem. We know that loading is very essential as a link in the logistics chain as a whole. And we also know that there is a huge amount of labor shortages in that area. It's very hard to find people who are skilled enough to operate the machinery that's needed to process and to load stuff. At the same time, we know that if we would automate it, we would most probably be able to increase productivity and efficiency. And at the same time, we would be able to increase safety because we can, in a lot of processes, make the human be outside of the area of danger. And at the same time, we also hope that we would just have less accidents by having an automated system. So where I'm coming from is the large-scale robotics lab. That's also the philosophy we have there is that we don't think about our working machines, such as cranes or forklifts, as machines, but we think of them as robots. And in order to think of them as robots, we have to model them accurately enough so that we can control them as if they would be robots. Meaning especially that we have to be able to model the hydraulics and the difficult parts in such a system to such an accuracy that we can treat them as robots. So we can see this is our open-air test site for autonomous machines, where we test a lot of machines. And here you can, for example, see the forklift, and we have a container and a very nice setting here to test and run these machines and develop on them. So what's the current state of the art? If we think about the last mile, we have structured environments where this problem is more or less solved, the automated loading, especially with forklifts. These environments are optimized for logistic operations as a whole. Usually you have some kind of pre-planned routes in warehouses, and you have very trained personnel which can easily operate what is left to do there, and which are usually out of the way of the autonomous machine if necessary. And on the other hand, we have unstructured environments. Most prominently, I would say, construction sites, where we also have loading operations going on. And we want to slowly approach these very unstructured, ever-changing environments and be able to map them, to reactively navigate within them, and to do that reliably and safe. And at the same time, we want to be able to deal with all the challenges that go hand in hand with this, especially weather conditions, light conditions, and also mechanical issues. So if we think about the harsh conditions and what that means, we can see the following things. One thing is that we have more or less weather-related things, such as it's very sunny, therefore hot, it's very rainy, or it snows, and things like this. But we also have elements that are very hard in a different way, such as reflective puddles, where even LiDAR and camera show huge artifacts usually. And we have slippery and bumpy ground, which are mechanical effects that compromise the operation of an automated system in that area. So if we think about this, we have a lot of variety and problems we have to tackle. So what we started first was we tried to catalog them over years, first for vision, then also for LiDAR. So we have done that over many years, and we most prominently presented this as the Robust Vision Challenge. That was in cooperation with CVPR, ECCV, ICCV over many years, where we cataloged all these problems first to then be specifically able to tackle them. So if we now think about the last mile delivery, what we can see is that if we think of the system I'm going to present, then we think of a situation where we have a different situation every time. And that is very well represented by the system I'm presenting here, which is a truck-mounted forklift, which is going to be mounted at the bottom of a truck and taken with the truck and can then operate in a completely new environment, completely autonomous, without any loading infrastructure other than itself. And this gives a lot of chances for delivering processes in the future. So, and what we want to do now is we want to automate these things. So what we see here is a picture of our forklift in the test area of Digitrans, where we tested it under rain conditions. And I will now introduce some of the components. We have an all-weather obstacle detection. We also continuously test new sensor technologies. In this case, for example, we have a radar system and infrared baseline. Then we, on the front side, have like a multimodal object detection system for the most important features such as pallet detection and loading platform detection. And we have in the core of this all an intelligent automation system, which is then very much in control of this high precision planning and control system that runs all the actuators of the system. So if we look at the field of views, this is what we have. We have like collision detection sensors on one side, and on the other side we have object detection sensors. And the reason for that is that the system is driving in one direction and loading in the other, which we will see soon. So here's now how we tested it under rain conditions. I mean, there are many tests like this, but this is a setup where you can regulate the amount of rain. It looks as if it would not rain very much, but if you stand there, you would feel very different. Yeah, and we found out that our system for obstacle detection, which is more or less an adaptation of a system that we have been developing for a braking system for tramways over many years, is very robust against rain as a hampering factor. Far more robust than most of the other systems we tested. So, and the reason for that is that it's it has 3 cameras and has explicit inbuilt rain coping mechanisms in the stereo system itself. So in the very early steps of the stereo. Okay, now the pallet detection. Obviously, if we want to move pallets, we have to detect them. Usually we think of Euro pallets for now. What is the difficulty here? That they look very different at different age, but also in different weather conditions, if they are wet or if they are old, and all these things have a huge impact on the appearance, which made us think that we should go the direction of going more in using the geometric features as a main anchor for the detection, and that's what we did. And we did so by using only geometry-based detection features, which combine a bottom-up and a top-down approach by representing first geometric elements such as edges and corners, and then connecting them in the deep learning network itself to give a complete response for the entire entity of a pallet. So it's a bit similar, the network, if anybody knows, to CenterNet from the voting mechanism, but it has a lot of other features for the edge detection, for example. And once we trained this on purely synthetic data, we could use it on real-world data quite well, and we were very surprised in the beginning, and it gave us the huge opportunity to run it again and again. Whenever we found problematic situations, we just created new synthetic data and evolved on that. And now we have a very controlled mechanism for creating this data for outdoor scenarios, also for other problems actually. At the same time, we need some intelligent automation system, and here I want to emphasize one thing, that this has to work with a human also. So we have these problems with the system that usually you sometimes want to be able to tell the system to change either something or to stop something, and in order for this to work, to have like robust fallback mechanisms also for human intervention, you need to have some kind of more or less undo mechanism in the behavior. So for example, if you load a pallet and it was the wrong pallet, you want to put it back before you take another one. And these things are very important. You don't think about this at first, but once you start to really develop a UI for these systems, you find out that this is essential for being useful. And that's also what we found out in our user studies. So that's one of the important things. I mean, there's a lot of adaptability in the behavior, especially regarding mechanical mechanisms we will see later. and we wanted to build a system that we know how it works. It was on purpose not completely AI driven, but after like a recipe, so that we know what it does and when, because we need this trustworthiness in that case. So, and obviously we needed some path planning. I'm not sure. Sorry. Video does not play. Second. Yeah. Doesn't matter so much. Okay. On the left side, we see that for the path planning, we have an approach which replans all the time. Whenever we give the system a new query, more or less, consisting of a palette to pick up in the current position, it will determine completely new paths within the environment, which is already mapped in that case. So this means that for every palette, the path is planned anew, and there's no like pre-built paths, but they are optimization based. And it's real-time capable, and we can see here already that it works together with the with our control mechanisms to then in the end pick up the pellets. And here it's I have to emphasize that this hydraulic actuation is something where you need to model the system in a detail which is not common for robotic systems, for example, which are usually driven by electronic motors and not such hydraulic mechanisms, which are far harder to model. Oops. Also, the user interface has been designed in a way that we know that it works with a human, so this has all been verified. User studies have been made, and we did continuous tests with experienced forklift drivers of different age and gender, and did like a complete evaluation. And if we now look at the results of this, we can see that there's several sensor systems, and we have this forklift with the user interface completely operating according to plan, where we select the amount of pallets we want to unload and load from A to B, and then the operation starts. So I will now switch to a more detailed view, which is the inside view. And what we see here is how the planning for loading from one loading area to the other loading area happens. So all the pallets in this area will be put here in the end. And we are now able to run such scenarios with a 99.5% success rate. So we are getting there. But obviously there are always things to be done. One thing which is not very good currently is that we are not very good at snow, especially due to the change in friction, which we can't deal properly with currently. But that's the next thing we want to tackle in this winter. I want to just emphasize on one more thing here. So here we can see something which is very important for robustness, that we use the mechanical sensors also as a feedback for the system control. For example, here the forklift, its fork more or less feels where the loading platform is and then goes up and out of it. And whenever we could do things like this, they are far more robust than everything we could do with any sensor. So the tactile measurement is very accurate usually. Here we can also see how it can deal with problematic situation and self-correct. So in the behavior we already employed a lot of correction mechanisms and robustifications. Okay, so thank you very much, I think.